Okay, example 7. Paddling with the current in a river, Jake traveled 16 miles. Even though he paddled upstream for an hour longer than the amount of time he paddled downstream, he could only travel 6 miles against the current. In still water, Jake paddles at a rate of 5 miles per hour. What's the speed of the current in the river? So the genre of problem this is, it's a uniform motion problem. More specifically, it's a boat in the river problem. Okay, and there's, depending on how they feed you the information, there's different ways to do it. But anytime you have any vehicle being acted upon by outside forces to either make it go faster or slower, it's a boat in the river problem. It could be an airplane in the jet stream problem. It could be a jet stream in the, jet ski in the water problem, whatever. Some vehicle is being pushed by some current. That's what type of problem we're dealing with here. So the first thing you want to focus on in these problems is you want to establish two specific rates that are going to be affecting the rate of the vehicle. The first rate is the speed of the boat in still water. If it's an airplane with no wind blowing, all right, so again, how fast can the vehicle go if there's no forces acting upon it? Still water rate. Sometimes they tell you, sometimes they don't. If they do, I write that number down. If they don't, I usually call this B, the letter B. So it says, in still water, Jake paddles at 5 miles per hour. Okay. The other speed you want to know is the speed of the current. Again, sometimes they tell you, sometimes they don't. If they do, write that number down. If they don't, I usually call this one C. All right? What is the speed of the current in the river? They're not telling us, so that means we don't know it. So C miles per hour is the rate of the current. Okay. Now, I don't teach physics, I teach math. In math, we just keep things simple. In physics, they have other forces acting upon things. But for the sake of this class, assume that if you're going downstream, that the speed of the current is pushing you that much faster. If you're going upstream, the speed of the current is pushing you that much slower. So it's going to add or subtract your rate. So if I'm looking at this and I have upstream and downstream, and I'm assuming that we all have some experience maybe floating down a river on a canoe or a inner tube or whatever, or maybe going on a boat or whatever, cow tank possibly. But upstream means you're going against the current, downstream means you're going with the current. So upstream slower, downstream faster. Okay? So if I were to fill in my rate, time, and distance in this problem based on these categories, the upstream is how fast I can go without anything acting upon me, minus how fast the current's pushing me backwards. Order matters. It's always the speeds in still water minus the speed of the current. Always put current second, put the boat first. Whether you know, no matter what numbers you know, boat speed first, current second always. Going downstream opposite, we're going with the current's pushing me faster, so how fast can I go by myself with no help, plus how much help I'm getting. The other thing I happen to know here is that he travels 16 miles with the current, which means downstream, so 16 miles is his downstream distance, and he can only paddle 6 miles against the current or upstream, so 6 miles is the distance here. They do give me a relationship on time, but I don't want to do that way, so let me just real quick focus on that for a second. He paddled upstream for an hour longer than the amount of time he paddled downstream. So if I were to just put this category here, or this equation here, time upstream equals time downstream plus 1. Okay, that's what the highlighted sentence is telling me. So if he paddled for 7 hours downstream, he would have paddled 8 hours upstream. All right, whatever the times come out to be. All right. So for now, I'm going to just call this his upstream time and call this his downstream time. Again, just because that's where they are, upstream top, downstream bottom, right? So what I want to do is I want to come up with an expression for these two things to put into this equation in order to figure out what they're asking me to find. Okay, and what they're asking me to find is what's the speed of the current. They're asking me to find C, right? Using my basic rate times time equals distance idea, his upstream rate, which is 5 minus c, times his upstream time we don't know, is equal to his upstream distance of 6. So I can get his upstream time to equal 6 over 5 minus c. His downstream speed, which is 5 plus c, times his downstream time, which is t sub d, is equal to his downstream distance, 16. Rate times time equals distance. Divide both sides by 5 plus c. His downstream time is 16 over 5 plus c. This is hours because this was miles per hour and this was miles, so this is hours. And once I get these expressions for t sub u and t sub d, I'm going to just transfer them over there and put them in place of those. I'm going to put the c expressions in place of the t expressions because I want to find out what c is. So, if I do that, 6 over 5 plus 5 minus c, leave some space, equals 16 over 5 plus c, leave some space, plus 1. T sub u is that equals T sub d is that plus 1. Just a quick little substitution. And now I'm looking at a rational equation trying to find out what c equals. And the denominators are 5 minus c and 5 plus c. And you'll notice that 5 minus c and 5 plus c are completely different objects, right? So least common multiple is simply the product of those two things. So I'm going to multiply each object by 5 minus c times 5 plus c. Do be aware that 1 is still part of the problem, so 1's also being multiplied by it even though it's not a fraction. So each and every term, fractions, non-fractions alike, all get multiplied by that common denominator. We cancel before we multiply, so this 5 minus c cancels that 5 minus c, leaving me with 6 times 5 plus c. This 5 plus c cancels that 5 plus c, leaving me with 16 times 5 minus c. Nothing cancels here, leaving me with 1, which doesn't matter, times 5 minus c times 5 plus c. So we successfully get rid of all the fractions. Now we simplify. We're going to multiply distributive property, some FOIL going on over here. So 6 times 5 is 30. 6 times c is plus 6c. 16 times 5 is 80. 16 times negative c is negative 16c. And then 5 minus c times 5 plus c is 25 minus c squared. I recognize the difference in squares structure, factored form, so I simply wrote down the difference of squares that would be. Otherwise, you can FOIL it. First times first makes 25. Outside 5c, inside negative 5c cancel. And last times last is negative c squared. All right, I do have a quadratic expression. It's got c squared in it, so everything equals 0 is your best bet. The lead term, the c squared term is negative. I like it to be positive, so I'm going to move everything to the left. So I'm going to make the negative c squared come over as positive c squared. Got a negative 16c becomes positive 16c. I got positive 80 plus 25, that's 105, so minus 105. So my end result in descending order is c squared plus 22c minus 75 equals 0. All right, and then finally, I could look to factor it. If I can't factor it, then I can always do the quadratic formula. But can everybody see that 25 times 3, 25 positive, 3 negative, makes the proper product and proper sum? So c plus 25 times c minus 3 equals 0. Before I jump to the quadratic formula, I always look to factor it. Especially, I mean, 75 is a little bit larger, but it's still a pretty friendly number. It's 1 times 75, 3 times 25, 5 times 15. It's not that hard to find a few pairs of numbers and multiply to make it. Just go through the basic ones, and if you happen to find it, that's great. So that means either c plus 25 equals 0. Remember, after you factor, you always set it equal to 0 to figure out what the answers are. So even though positive 25 and negative 3 are the correct pair of numbers, when I go to solve it, I move the 25 across, it becomes negative, move the 3 across, it becomes positive. So C is equal to either negative 25 or positive 3. Now, we have extraneous roots. We talked about that yesterday. One reason for extraneous roots is that, for example, 5 or negative 5 in this case would create 0, right? So one of those would be irrelevant, right? If we got those answers. The other place where extraneous roots come into play is when you have a particular problem like this, that the answer has a meaning. And if that meaning is ridiculous with the answer, you throw it out. We're looking for the rate of the current, right? Negative 25 miles per hour, does that seem reasonable?
No.
No, it doesn't. So since we're talking about the rate of the river, rivers run with a positive rate. So if we get a negative rate there, it just doesn't make sense. We can throw that out as extraneous because of the context of the problem. So the correct answer here, the rate of the river is 3 miles per hour. Now these are checkable. You can make sure all the stuff that's supposed to happen happens. Watch this. If C is equal to 3, what's 5 minus C? 5 minus 3 is? 5 minus 3 is 2, right? What's 5 plus 3? 8. 2 times what makes 6? 3. And 8 times what makes 16? 2. And the upstream rate is supposed to be one more than the downstream rate, right? So the answer of 3 makes everything happen as it should with that chart, right? 5 minus 3 makes 2, 5 plus 3 makes 8, 8 times 2 makes 16, 2 times 3 makes 6. Upstream time is one more than downstream time. Everything that's supposed to happen with those numbers. So it's a quick check that you can do on those to verify. I did tell the other class that I'm most likely not to put a problem like this on a quiz. It's a challenging problem. Homework, I don't mind putting it on the homework. The practice problem in the back actually deals more with rate of work as opposed to rate of speed, so it doesn't fit this exactly. But there's still some solving a rational equation structure in that problem, so you'll see that some work like this is on there, but the setup is a little bit different from the one in the back.